Hello guys, in this video we're going to be talking about the remainder theorem for a quadratic equation. Now imagine you are given the general form of a quadratic equation to be divided by x minus p using long division, and this, like I've said, is the general quadratic equation, and p can be any whole number, be it negative or positive. Now if you have watched my video on the long division of polynomials, this is a polynomial being divided by this. Now if you follow this series of steps that I have listed down here up to this last step here, and you do your mathematics quite all right using the long division process, you will discover that this becomes the remainder. AP squared plus BP plus C is the remainder. Now, this is what the remainder theorem is talking about. That if a quadratic is divided by x minus p, where p is a whole number, that the remainder will be this. Now, let's look at something else. This is the remainder theorem for a cubic equation. Now, if you divide a general cubic equation, which is ax cubed plus bx squared plus cx plus d, by this same x minus p, where p is a whole number, being negative or positive, by long division. Now, and you follow the same steps which I have solved here. Like if you have the knowledge of long division, if you haven't watched my video on long division, try and watch it, and you will get the understanding of how this came about. So you will discover that this will be your remainder. Now, this is still the same thing that the remainder theorem is talking about, that if a cubic equation is divided by a factor of x minus p, the remainder will be this. Now, in an algebraic expression or equation, the remainder is not actually useful, but it is always important because it shows us if x minus p is a factor of that particular cubic or quadratic expression. Now, let's take this for example. This is a quadratic equation to be divided by x minus 2. Now, we can see following the long division process that we got 8 as our remainder. This shows us that x minus 2 is not a factor. And instead of going through this long division process, we can just apply the remainder theorem to look for the remainder, which is 8 here, using the remainder theorem for the quadratic equation here. And we can likewise do the same for a cubic. Now, this is a cubic expression being divided by x plus 2, then we can see that the remainder is negative 2. This shows that x plus 2 is not a factor of this equation. Now, we can try the remainder theorem for both the quadratic and the cubic equation and see if it actually gives us what we are talking about. Now, let's say first one is x squared plus 3x minus 2. Then using the remainder theorem, divide the above quadratic by or rather not divide. Let me cancel this. This will lead me to using the long division. Using the remainder theorem, find the remainder in the above quadratic when it is divided by x minus 2. So now this is the question. This is the quadratic. Using the remainder theorem, find the remainder in the above quadratic, which is this, when it is divided by a factor of x minus 2. Now, instead of going through this long division process here, we can just apply the remainder theorem for a quadratic which looks like the general quadratic expression, or the general quadratic equation rather. So solution, and it is in this form: ap square plus bp plus c. Now here we can see that a is equal to 1 from here, while b is equal to 3. That is what we are seeing here, while c is equal to negative 2, and p is equal to 2. When you set x minus 2 to 0, you get x to be equal to 2. So this is also the same when you set this factor to x minus p. Taking p to the other side, you get a positive p, which is what we got here. So p is equal to 2. We impute it in the equation. We have 2 square plus 3, 2, that's the p here, minus 2. And now we can see that this gives me 4 plus 6 minus 2, and this gives me 10 minus 2, which is equal to 8. And now from here we can see that it works perfectly by just imputing values into the remainder theorem and getting your answer to be 8. Now, like I said, let's assume our answer was given to us as 0. It will show that x minus 2 is actually a factor of the quadratic when you are trying to use uh, factorization to get the factor of this quadratic. Now, what about the cubic? Now, for the cubic, number 2, we have a cubic 3x cubed plus 2x squared minus 5x plus 4. And we are asked to look for the remainder when it is divided by x. Asked to look for the remainder when it is divided by x plus 2. Now, applying the remainder theorem for a cubic expression, which is what we are seeing here, it looks like the general cubic, which is up here. It looks like the general cubic expression, only that the x terms have been replaced by p. So you don't have to cram it. Solution. Now you say by the remainder theorem, which is a p cube plus b p square plus cp plus d, where a is equal to 3, which is the first term here, b is equal to 2, c is equal to negative 5, and d is equal to 4, while our p here is equal to negative 2. Setting x plus 2 equal to 0, we discover that x is equal to negative 2 and x is equal to p, because we have switched the x terms into p. So x will be equal to p. Then applying this, we have 3 negative 2 cube plus 2 negative 2 square plus, or rather minus c, which is 5 negative 2 plus 4. Now this will give me 3. This will give me negative 8 plus 2. This will give me 4. Positive 4. This gives me positive 10 plus 4. Now this gives me negative 24 plus 8 plus 14. And now we can see that 8 plus 14 is actually 22. So this is negative 24 plus 22, which comes out actually to be negative 2. Now we can see that the remainder theorem works perfectly for the cubic expression also. And so this is like a shortcut only when you are asked to use the remainder theorem. So instead of using the long division method to look for a remainder of a particular cubic or quadratic expression, you just use the long division. And like I said, when the remainder is 0, it shows that that particular divisor is a factor of that equation. Now we can take one last example where the remainder is 0 to really get what we are trying to see. And if you have watched my video on the factor theorem, you will discover that I use this same example in solving for the factor theorem, which is x cubed minus 2x squared minus 5x plus 6. Now, if you are asked to find the remainder of this particular cubic when it is divided by x minus 1. Now, you should write solution, and by the remainder theorem, ap cubed plus bp squared plus cp plus d, where a is equal to 1, b is equal to negative 2, c is equal to negative 5, and d is equal to 6. And our p is equal to 1 when you set this to 0. Now, we have our p to be 1, which is 1 cube, and our b is negative, so I'll have negative 2, 1 square. Our c is also negative, I'll have negative 5 multiplied by 1 plus our d is 6. And this will give me 1, negative 2, negative 5 plus 6. And this actually resolves to being 0. Now we can see that since our remainder here is 0, it means that x minus 1 is actually a factor of this cubic expression. And we can try other values ranging from 1, and you will discover that x plus 2 is also a factor when you impute negative 2 as the p, and also that x minus 3 is a factor. So this is what the remainder tells us. If I impute a positive 3 into this equation expression rather, my answer will be 0. That shows that x minus 3 is a factor. And if I impute my negative 2 when I set this to 0, if I impute my negative 2, my answer becomes 0 for this cubic expression, and that shows that this term here, this and this, are all factors of this cubic expression. Now, don't forget to like, share, and subscribe for more videos. See you next time.